close I can. We are just in the beginning, right? It can get harder. We are talking about circuit with a few resistors. So later on, we'll see circuit with not just the resistors, also the inductors and capacitors. When you look at the circuit that you are using every day, your cell phones and the iPod, everything, that has chips, that has circuits with thousands of transistors, plus the resistors, plus the inductors, plus. So we are at a very fundamental level. Okay, so let me review very quickly what we have done. Right? And you should, what are the basic concepts you have to know at this time? Right? Okay. First of all, you need to know the concept of the series connection and the parallel connection. Got it? Okay. Now that's very simple, right? Okay. Series connection, parallel. Yeah.
Can you maybe review the definition of like how you define a node in the circuit?
A node is the joint point of two or more components. Yeah. So this is a node.
Because the book would say that like it sometimes we'll talk about like the whole top branch as being a node and the whole bottom branch as being a node.
Yeah. Well, let's see how if I have this, okay, yeah?
Right.
Okay. How many nodes do we have? This is a single node. Yeah? The whole thing here is a single node. Yeah? Correct?
Mm-hmm.
Yeah. Or I can draw a different way. Right? Okay, that is a node.
Okay.
Of course, everything on the bottom, you like connect this right here. That is a node. It doesn't matter the shape of the connection, as long as the, these are what we call the metal line. Metal line. As long as the metal lines are joining together, that becomes a node. Okay. So you've got to understand the concept of the series connection and the parallel connection, right? And you need to be able to recognize what is a series connection and what's a parallel connection. That is the fundamental of the fundamental. Okay. Then we talk about several important laws. Right? Ohm's law, very simple, right? Current is equal to the voltage divided by the resistance. Right? Okay. And then we talk about the Kirchhoff voltage law, KVL. We talk about the Kirchhoff current law, KCL. And from the Kirchhoff voltage law, we could derive what we call the voltage divider rule. And I gave you the formula already. And from the Kirchhoff current law, we could derive the current divider rule. And then I have solved some circuits in the class based on these different rules and laws. That's it. I didn't do anything else so far. You will see more later. It'd be nice if you can end the class right here. That'd be awesome. Okay? All right. Now the weekend is coming up, and also Monday is holiday, so you need to spend the time to try to catch up. Right? I did an example at the end of the last lecture. Now if you can fully understand the example, then you are in very good shape so far. Huh? So far.
So far.
I cannot predict the future. So far, right. So I'm going to start with today we're going to start with circuit with dependent sources, and then at the end of that, that will be the end of chapter 2. I'm sorry. Is it chapter 2? Where are we now?
Yeah, chapter 2.
We're at chapter 2. Okay. So on Friday we're going to start on chapter 3.
There's no. Oh yeah.
Right?
Yeah.
On Friday.
Yeah.
We're going to start on chapter 3. And it takes about, I would say, about 2 to 3 weeks before we can finish chapter 3 and 4. So that means toward the end of September, we will have the first exam.
Could you possibly do an example with multiple current sources?
Yeah, I can. Why don't I finish up this topic I mentioned, and then I can go to the homeworks,
Yeah,
right, in the
be
book, and give you some guide, some hints, right? Okay. And if you have any question about any homework, you can let me know. I can try to I cannot solve it for you, right? I can give you some help. And actually, any homework problem in the back of the chapter you want me to try to solve for you, I can do it for you. If you would like me to do it. But provided that is not the one I have assigned, right? Okay, so we're going to talk about a circuit with dependent sources. Right? Up to this point, all the circuit we have
Independent sources.
talked about have independent sources. But now we're going to see some circuit with dependent sources. Okay. Now, as I mentioned in the beginning of the semester, there are two types of dependent sources. Okay, that's the symbol of the dependent voltage source. Okay, and then this is the symbol of the dependent current. So why are they called the dependent sources? Because the values of these dependent sources depends on something else. Okay, so let me do a couple of examples. So let's say we want to find I1 current and the voltage V sub.
Professor,
Yeah,
is that 200 on the top?
yeah, 200 times I1. So So you can see now we have a circuit that has two resistors, right? 3K, 5K. We have a independent voltage source of 12 volts, and we have a dependent voltage source. And the value of that voltage source is what? Is 200 times I1, and I1 is the current right here. So now you can see why it's called dependent source, right? Because the voltage of the source depends on the value of I1. All right. How do we get started? Well, this is a single loop, right? And when you see a single loop, the best way to do it is to use the KVL, the current called voltage law. And then according to KVL, the sum of voltage rises and drops equal to 0, right? Okay, so if you use KVL, right? Then you have to start from any point, and then go around the loop and go back to the same point. So let's say if I start from this point, starting point, and I go around the loop, I go back to the same point. Okay, and I'm going to write down the equation that has all the voltage rises and drops. Right? Okay. Now, so I already gave you the direction of the current. So therefore, what is the voltage polarity on the 3K? If the current going this way, then the voltage polarity must be plus and the minus. Huh? Okay? Now this one is already given already. And this one also plus and the minus. Right? So you have minus 3K I1, right? And then this becomes a voltage rise, right? So plus 200 I1, and this is a drop, right? Minus 5K I1, and you go around here, that is a rise, plus 12 equal to 0. Now you have one equation and one unknown, right? So you should be able to solve that unknown, right? So I1 what? Minus 3,000, right? K is 1,000 plus 200 minus 5,000, right? Equal to minus 12. So
Minus 8,000, minus 7,200, no.
So you can get I1
Minus 7,800.
equal to, well, can I make a correction to make it easier?
12.
I'm going to change this to 2,000. Okay? 2,000. 2,000. So that would get a nice number. Okay?
So that's
So-
minus 6,000.
You do this calculation, you find I1 is equal to 2 times 10 to the minus 3 n. And this is called 2 milliamp. Right? Okay, then this law is the voltage on the 5K ohm, right? So therefore it's equal to I1 times 5K, correct? So 2 milliamp times 5K give you 10 volts. So that's it. That's how much. Huh?
TI later.
Can we do one more
That's
example?
Oh, that's cool. It uses the ROM. The what? It uses like the actual calculator ROM. All the it has all the built-in like cosine, tangent, all that. That is cool. Still not as good as the original ROM.
So that's what?
Still not as good as the original, but
Oh, really?
it's nice just on the go.
Too bad they won't let you use it.
Yeah, yeah.
Do you have to pay for it, or do you
No, it's free.
just free?
You just have to get the ROMs from like BitTorrent or something.
Yeah. Oh, so you should have paid for it. What are you trying to say?
Well, yeah, usually someone will rip the ROMs from the
Yeah.
calculator, like dump and stuff. It's kind of like the Super Nintendo emulators, stuff like that.
Problem of using emulators on the iPhone is it slows the shit out of it. So I took it off. It wasn't worth it for me.
Alright, so let's say I want to find these left. Again, when I put a symbol like this, that means this node is connected to the ground. This is the symbol for the ground. Ground means the voltage is 0, right? Potentially. Okay. Now you can see that this is a parallel network, right? So when you see a parallel network, you would probably want to use the KCL. The Kirchhoff current law. Because basically this is a node. Huh? This is a single node. And from the KCL, you can write an equation that will summarize all the currents entering and leaving the node. And that sum has to be equal to 0. Right?
Where's V0 at?
What? 0 or what? 0 voltage?
Yeah, no, V0 or VO.
Oh, V0. V0 is right here.
Oh, okay.
So you can see that this current, this current
It's dependent.
is dependent on this voltage. Yeah?
Okay. So you don't need a battery sign over where V0 is?
I don't need a I do
Yeah.
have a independent source
Okay,
of 2 milliamp.
okay.
Yeah.
Oh, okay.
Yeah. Now, if I take this away, this circuit will not work. Because it does not have any. It's like you want to generate some power, but you don't have the sun or you don't have the electricity.
Okay.
Okay.
Gotcha.
This circuit is a little more difficult than the previous one, but of course it can be solved. Huh? Okay, so according to the notation I had here, the voltage here to the ground is what? Is V west, right? Okay, that's the voltage from here to the ground. Okay, so therefore, if you have a voltage like this, you should have a current, right? According to the Ohm's law, yeah? So this, let's call this I prime, can I? And there should be also a current. If this is Vs, this also should be Vs, right? Because it's parallel, okay? The voltage across the parallel network is what? It's always the same, right? Okay. So therefore, you should have a current. I'm going to call this I double prime, can I? Okay? So now you can see we have 4 branches. Therefore, we have 4 currents entering and leaving the node. Right? So there's a current, right, in this direction. There's a current in that direction. Okay. So now you have to make a sign notation. So let's say if the current is entering, it becomes it's positive. The current less leaving is negative. So I have VO over 2000. Of course, the unit for this is N, huh? Okay. So that's entering, right? Plus sign. And then this one is leaving, so we give it a minus sign. Minus what? V sub S over 6K, correct? Again, this is the current, huh? So it should be the unit of N. And this, of course, is the unit of volts, yes? Okay, what about here? Minus V sub S over what? 1K plus 2K, correct? Because these two are in series, huh? Right? So the current is the voltage divided by the sum of the two resistors. Okay, then I have plus 2 times 10 to the minus 3, right? Because all these are unit in N, so this is mini N. So I need to put 10 to the minus 3. And that's equal to what? 0. Alright, so unfortunately, now you have an equation with two unknowns. And from your mathematics, you should know that you cannot solve this type of circuit, right? This equation. So therefore, you have to try to reduce the number of unknowns to one unknown, right? This law is related to V sub S. Why?
They're parallel.
Right? The voltage across these two is V sub S, correct? And this is V sub O. So V sub O is a portion. It's a portion of V sub S. And if you remember the voltage divider rule, huh? The voltage divider rule will tell you that V sub O is equal to V sub S times 1K plus 2K and then 2K. Do you remember that formula? Huh? Let me remind you again. Okay, let's say I'm putting a more general case. Okay? Let's say you have 3 in series, and the total voltage from here to here is, let's call V, right? Okay, and then you have R1, R2, R3. Okay, and the voltage on R1 is called V1, the voltage on R2 is called V2, the voltage on R3 is called V3. Yep? Okay. First, you should know that V should be equal to V1 plus V2 plus V3. Right? Is it correct? Okay. And according to the voltage divider rule, you can express any one of this voltage in terms of the total voltage V. Okay, let's say you want to express V3. So V3 can be expressed as V times the sum of all the resistance, and then with R3 on the top. Yep.
Is that supposed to be V3?
This is V3, right?
Yeah.
And the same concept applies to V2 and V1, right? So now you can see this equation came from that formula. Huh? Okay. So now I can put this back in here. Yeah? So now if I substitute V0 into here, I will get what? I will get VO, which is V slash S, times 2K, right? And then what? 3K times 2,000, that becomes 6 times 10 to the 6. Minus VS 6K, right? Minus VS 3K plus 2 times 10 to the minus 3 equal to 0. You understand this one? All I did was I put this into here, right? So you have a 2K on top, right? 2K, so that's 2K. And then VS right here. And then this will have to multiply to that, yeah? Again, this is algebra. Huh? Okay. Now you have to solve this one, huh? Do I need to go through that?
No, really.
Okay, I need to simplify something, right? So I guess I can cancel this, right? So 2K, this is 6K, right? No, this is not 6K, this is 6K and the K, huh? 10 to 6, right? So what do I get?
It's 3K.
3K. Good. Okay, now you see there's a common, we have to find a common denominator, right?
Yeah.
Okay,
6.
so what's the common denominator?
6K.
Right? So you multiply 6K, right, to the equation. You'll find 2VS
Professor,
minus VS, huh?
can you just cancel out VS over 3K? Because you have two. You have one that's minus and you have one that's positive.
Where? Here?
Yeah, that one and the other one.
Which one?
The third one. VS over 3K?
Yeah, that's negative and the other one's positive. Can't you just cancel it out?
Did you cancel out? Oh, wow, that's even better. Okay. Well, it will show in the equation on the right?
Yeah.
Okay. So, I did not notice that. All right. So I get 2VS minus 2VS, right? Okay. Equal to, I take the constant to the other side, minus 2 times 10 to the minus 3. Okay, as you said, this
You have to
cancel.
multiply it.
They make it easy. So this rest becomes 2 times 10 to the minus 3. And again, this is in volts, right? So that means it's 2 millivolts.
Yeah, but you needed to multiply the 2 by 6K
Oh,
as well.
I forgot to multiply that.
Yeah.
Oh, wow, that's a mistake. Okay, so that give you what?
12 by
No,
10 to the
no,
negative.
Okay, so it becomes
Still times 10 to the negative 3. Oh my god.
huh? What was 6K? 6K,
Oh, yeah.
right?
Yeah.
So this is become 12. Yeah, 12. So it's 12
Yeah,
volts.
never mind.
12 volts. Yeah? Okay. So we have found that. So we have found these rest. Hmm?
Can see some
How
bonds.
does he get?
How does he get what?
Okay, so he did the V0 with VS.
Yeah.
And then he stuck this where V0 is.
Yeah. Everywhere that's
Oh,
V0 So they'll have one variable.
So you have VS times 2K over 1K.
Now,
So
So VS over 6K stays the way it is, and VS over 1K times plus 2K stays the same.
I double
But
prime,
the first one
then you can just use this, right?
becomes
Because I prime is equal to V
replace
sub
the
S
V0
over
with
6K,
the
right?
VS 2K
I double prime
1
is
plus
V
whatever.
sub S over 3K. Huh? Okay, so with this, I have finished chapter 2. Now I'm going to go to the homework. On the back of chapter 2, and let me see if I can find some problems. Yeah.
Oh, sorry. That's supposed to be multiplication.
Yeah.
Actually, would that 2K
Oh.
Huh?
the VO equals to VS times 2K over 1K?
VO for this one right here? This one?
Yeah. Wouldn't the 2K be 1K? Because you want to find the VO, right?
Yeah, no. So it's 2K.
But from yesterday, you,
Yesterday, it was a different rule. That was the current divider rule. The current divider rule will be the opposite. This is the voltage divider rule. So the formulas are different.
So how do we get 3K out of VS times 2K?
Okay. Now, before I came here, okay, I looked through the homework. See, Professor also
The first one?
So,
No, the one right below it.
some of the homework and
Oh, hold on one second.
I think I can go through some three of them, okay? So the first one I would like to go over is 2.19. The second one will be 2.42. And the third one will be 2.56, okay? Now, if you have additional ones, you can let me know. If I have time, I can go through, right? Okay, so let's first go to 2.19.
The one pretty good.
For some reason, the homework problems are trickier.
Oh,
No shit.
no shit. You don't say.
The VS SK is just trying to show what's above it. Just copied what's above. I don't know why he did that.
Do what?
But the first one is just VS over 3K. The second one is VS over 6K.
No.
I don't know why he rewrote it like that.
And I'm glad I found this homework because it is not very easy to do for you. Okay, so this is
Thanks for
A,
coming.
B, C, D, E, right? So in this circuit, how many of you done this homework already? You know how to do it?
I think so.
Okay, good. So let me go over.
I don't know if I got the right answer.
Okay, this is fine. Okay? The rest of you are not good.
You have a
So, how many nodes we have in the circuit?
What's the question?
We have 5 nodes, correct? A, B, C, D, E, 5 nodes, right? Okay. And we want to find the voltage V between node A and D. VAD. That means you want to find the voltage between node A to node D. Right? Okay. Now the resistance are not given, but the voltage on the resistance
we have amperage.
What do you do? Huh?
I went from A to B and worked my way to the left. So I took VAB, minus 3, and then I went from D to E to get to minus 3, and then E to A got minus 4. Which gave me VAB equals 7.
Actually, all you have to do, quite simple, is to use KDL. Right? Okay. So if I go from A to D, right?
And D.
A, D, right? 12 volts. This is already given, 2 volts. This is given, 3 volts. Right? Yes? So this is A, B, A, D. So therefore, it depends on which direction you want to go. It doesn't matter, okay? If you go this direction, that's okay. That's a loop, right? From here to here, that's a closed loop. Okay, so I'm going to assume the current is going this way, and this is some current I, yeah? Actually, you don't need I, because the voltage are given. So if I go from this direction, I'm going to sum up all the voltage rises and the drops, and to be equal to 0, right? Okay, so therefore from here, what do I see? I see a voltage rise. So my is plus 3 volts, right? Plus 2 volts, and minus 12, and
Minus VAB.
Plus. No, not equal, okay? The sum of voltage rise and drops are equal to 0. What is this? That's a rise.
Yes.
So it's plus VAB and equal to 0. Now if you put a minus here, you're going to get a wrong answer. Right?
So
that's
why
it.
didn't you consider
Right here you can
AD?
find out what is VAB.
Yeah, so VAB.
Now this is, so it's not that difficult, right? But if I want to find out what is the current in the circuit, that becomes more difficult. Right? So what's the current?
You couldn't do it the opposite way?
Okay, let me assume that the current is this direction, right? I. So I want to find I. So how do I find I? Oh, you know how to solve this?
Just add all the currents. Oh no, you don't have amperage.
They're all in series, so I just see, right?
Yeah.
And you solve for finding resistance.
Okay.
My question is, if you
So,
go that way to figure AD, isn't that going to be a completely different answer?
R1 plus I times R2.
Yeah.
Actually, if I go from here, okay, I'm going to start from here, this point, right? ABL, right? So I get what? Minus, right? Or plus. So like this, then the current should be what? Okay. It doesn't matter. It doesn't matter. Okay. Let's just assign the direction of current like that, right? Okay. So if I do that, then according to the direction of current, this is plus or minus, right? I'm going to call this V1 plus minus V2, right? And the current is going this direction, so it's plus minus V3, correct? According to the current direction, I have a sign. Huh? So it's that's a voltage drop, right? Minus, yes? And then minus 12, yes? Drop. And this is drop minus I times R3, and that's a rise, yes? Plus 4 equal to 0. Wow, there are so many unknowns, right?
Yes.
But this one is equal to what? It's equal to minus 3 volts. Huh? This one is, why is it minus 3 volts? Because the notation, the polarity I have assigned is plus or minus, but actually it's a minus plus, right?
Yeah.
So therefore it's a minus, VUY is equal to minus 3 volts because the polarities are opposite each other. Okay? And the second one is minus 2 volts, right? The first one is minus 3 volts. Plus 4 equals 0.
No, that's not right. It can be 0.
Yeah, because that's not going to equal to 0.
You cannot?
Yeah, it can be 0. 6, that's negative 4.
Okay, that's it. This is minus 2, that's minus 5, minus 8. Yeah, sure, it's 0, yes.
No, it's what?
Huh?
Professor?
It's negative 4.
What?
Yeah, but no. That is negative 3.
Right.
So plus and plus becomes, minus becomes plus.
Oh.
You admitted that. Okay, so
Okay, so therefore,
okay, so now we got 6. Yeah, okay, yeah, now it makes sense, yeah.
so now we have one equation. This equation has 1, 2,
This is what it is.
how many unknowns? 1, 2, 3, 4. 4 unknowns, correct? But now I have additional 3 equations, so I got 4 equations and 4 unknowns. Got it? No? Okay, I'm going to spell this out. So I R1 equal to minus 3 volts, right? I
He lost me.
R2 equal to minus 2 volts. I R3 equal to minus 2 volts. So now you have 3 more equations, plus this way you have 4 equations, and you have 4 unknowns. And as long as the number of unknowns the same as the number of equations, you can solve for the unknowns. However you can solve it. Right? Well, you can make R1 equal to minus 3 over I, right? Put it in here. You can make R2, everything, you can put this in terms of I, right? You get one unknown. Put this back in here, you get one unknown. Solve for the I. That's it. Right? Okay, let me change the problem a little bit, right? So I can change it any way I like, huh? Okay, I'm going to... Huh? Okay, now just let me finish this. I go to 42. Now you can see in this circuit, the definition of the ground was never defined. Yeah? So that means if I want to define the ground, then the circuit will be quite different. Okay? So let's say if I want to define the ground, right here. If I define a ground right here, then I want to find out what is V sub A. Okay? When I say V sub A, that means V sub A to the ground. Got it? If the second substrate is not defined, then that second substrate is always the ground. Or I can say V sub A E. Now you know what's V sub A E, right? Why is it? Huh? For what, right? V sub A E. But V sub A to the ground will be what? Will be this, and that. Yeah? So what is V sub A? Is equal to 7 volts, right? Okay, now, if I change the ground to here, then that's a different story, yes? Right? Depends on which node is the ground. Huh?
Where's even 7?
Okay,
So it'll be a 9.
let's go to 5 minutes left.
You're still gonna find that.
Let's go to 2.1.
Dude, that already made no sense.
That's why I started texting. It's just gonna make me lost. Which one's it going to?
That's a 44.
Okay, I have to say this one is also a little tricky. Yeah.
Which one is it? I'm sorry, which one is it? 44 doesn't have that. 41.
Okay. So this problem lets you to find the equivalent resistance between the node A and B, right? The purpose of this problem is to test it, to really find out if you understand the concept of series and parallel connections.
Is this problem going to be on the test?
On the test? No, not this easy.
Oh, not this
Not
easy.
this
Bad house.
Okay. Now, this, if I redraw this, will make it easier for you to do the problem, okay? This is the same as that.
Only just wants you to find the resistance.
You see that?
I see.
If you can see that, then I think you know how to do the problem. Huh? Do you agree this is the same? Because this node, right here, that's a single node. That node now is right here. The same node. All I did was I pulled the node down. Yeah? It's the same node. So once you have that, these two are in parallel first, right? Okay, then these two are in series, and then that is in parallel with 5, and then quickly,
R2 and R5 are not in parallel?
yeah. So the next thing you do is you have this, right? So this becomes R3 in parallel with R4, right? And then what's next?
R2 is parallel with R5?
Yeah. Then you have R2, right? These
Yeah.
two in series.
Yes.
And then so the next thing you can do is this one becomes